on session number 4, evaluation of supervised trial data, estimation of maximum residue levels and STMR and HR values. I believe Dr. Caldas is going to continue wrapping up that session 4, and then she will be moving to estimation of dietary intake, which is our final topic for the series. We will again have a break around 10:20 today. So I will just be working with Dr. Caldas to determine when we should be taking our break, at what point, and when we have questions. I think that's about it. Should we just jump right in, Eloisa, and begin with your presentation where you left off yesterday?
Yes, sure.
Okay.
Good morning, everyone.
Good morning. Thank you, everybody.
What we could do today is finish the section 4 and then open for questions, because then we're going to change completely subject. So, and then we can close the subject with questions. Doesn't matter what time that would be before we start the new section, the last section. So is that okay, Jason?
That would be fantastic. Thank you.
Okay, we finished the last section talking about cropping, and I gave this example with metalaxyl in head brassicas with data in broccoli and cauliflower. And now, yesterday there were questions regarding processing processed commodities like polished rice. So I think this topic is very interesting because it concerns sometimes not the MRL, but the data that will be used in the dietary risk assessment. So it kind of goes up to that. Processed foods, food can be submitted to various processing before it's really consumed. Cleaning, peeling for inedible peel crops, cooking, juicing, brewing, canning, milling and baking, oil production, drying is just one of processing procedures that the food may be submitted before consumption. It's important to say it again that the maximum residue level concerns the food as it is traded. So not as it is consumed. So that's why it's so important, the processing studies to generate processing factors. We may start by defining what is a processing factor. So the commodities, the raw commodities submitted to a processing, one of those that are listed there, sometimes 2 of those. For example, you can have wheat, millet, and then use that wheat to make bread or to make pasta. So very different processing procedures because we really don't eat the wheat as it's harvested, but is how the wheat is traded. That's the same for other grains, for example, maize, many other grains. So that's why for grains, the processing studies are very important. Otherwise, you can have an intake problem just because you use a crop and the residues in the crop before processing, and just reflect something that it's really not real, because we don't eat, for example, maize. We don't eat raw maize. Maize should be submitted to processing to flour and then cook it before we eat it. So the processing factor is defined as the ratio between the residues in the processed commodity. It can be any processed commodity, divide by the residues in the raw commodity. We normally don't establish or recommended, estimate and recommended maximum residue levels for processed commodity when the processing factor is lower than 1. We only make that recommendation when the processing factor is higher than 1. That means there is an increase in the residues during processing. That's why the question that someone asked me yesterday, I don't remember the name of the lady, but it concerned polished rice. I think the question was that if I could use the MRL for rusted rice and apply the same for polished rice. Yes, the answer was yes, because actually the maximum, what you would expect in polished rice after the rice was treated according to GAP in the field is under the maximum residue level for the rice. But in some cases, we do have an increase in processing during processing. For example, the dry processing, when you submit the crop to a drying, for example, raising. Yes, normally the grapes are left in the field to dry out, and then you produce raise. And this is actually what happened in the field. There are 2 factors that happens during this procedure in the field or in an oven. You have water loss, the water is lost, so you have a concentration of the residues, but at the same time you have some degradation of the pesticide. So, what we have been seeing, and we do here in the laboratory, today I am in the laboratory, we do conduct processing studies for pesticide, for mycotoxins, and what we see here during the dry processing, the concentration of the pesticide during the loss of water, it's more important than the degradation. But you do have both processes happening there. For example, if we've seen some compounds that are photodegraded. So if the grape is left in the field to dry out, so you have the heat, you have the photodegradation, and you have also the concentration of the pesticide residue due to the loss of water. For example, tomato paste. Tomato paste, it's normally produced in the industry in an oven. So there you don't have any photodegradation, but you have the heat, and you also have the water loss, which will lead to higher residue in the outcome product. And so those are two crops, processed crops, when we normally expect an increase of the residues. But we have some other crops and food crops and also feed crops. I'm going to show you some examples later. And how do you estimate the maximum residue level for this processed commodity? You just multiply the maximum residue level, the MRL, because you may find strange, because sometimes I use the term level and sometimes I use the term limit. It's just because in the GMPR, you first estimate the levels and then you recommend the limits to the CCPR. So that's why in the text of the report, we have MRL, where the L is level, and we have MRL where the L is limit. So don't get confused, but assume it being the same thing, basically. So, so you just multiply the MRL of the raw commodity by the processing factor of that processed food. And then you find a MRL for the processed food. And you do the same for the STMR of the processed food. You multiply the STMR for the raw commodity by the processing factor of that processed commodity. And for the HR, it's just the same thing. And these values, STMR-P as the STMR, as well as the STMR-P, are used for dietary risk assessment. And I said it's very important to refine the dietary intake during the risk assessment. So that's why the companies, they are always looking for conducting studies, processing studies, because they know some compounds really don't leave any residue. So no residue, no high levels of residues are expected in processed food, but some residues, if they don't conduct processing studies and to generate processing factor so they can refine the STMR-P. And in this case, for MRL, you just estimate a new MRL for processed commodities. The processing factor is higher than 1. That means that if you increase the residue in the processed commodity, but for the STMR, you estimate in all cases. Mainly, it's important for dietary risk assessment if the processing factor is lower than 1, because then the STMR in the processed commodity will be lower than the STMR in the raw commodity, and that will be key for the refinement of the dietary intake. So here, just one example, actually, sorry, let me do something here so we can now see what it's behind it. Just a second. I meant to do that, but I forgot. It's very common to have a variety of processing factors for one single processing. Actually, I just, a paper of mine was just accepted in let me just show here. A paper of mine was, a paper of mine was just accepted in food chemistry, and there were processing studies over there in passion fruit. And what happened is that there were a large variety of processing factor when we peel the processed, when we wash the passion fruit, when we peel the passion fruit and just analyze the pulp, and when we dry the peel of the passion fruit, because the peel of passion fruit is being used widely in Brazil, and because Brazil is the most important producer and consumer of passion fruit, and the peel of the passion fruit is being used as a food supplement, because there are a lot of antioxidants in that, pectin, and also used as espessant in the food industry. And the reviewer of the paper was complaining because there were a large variability of processing factors that were generated, mainly for drying the peel of the fruits. And this is very common. You're going to see some data that I'm going to show later, because it depends on the initial residue of the raw commodity, and you cannot control the whole process and to guarantee that you're going to get always the same number after all. Additionally, you can have different processing steps for a given processing. For example, here you have a whole fruit, and you can here submit that whole fruit to different processing that would lead to the same processed comment. In this case, wet pomace, dry pomace, juice here, and here pressed pomace, dry pomace. This dry pomace is used as a feed commodity that can be fed to the cattle, and it will be considered in the dietary burden of the cattle, which will impact the final MRL of animal commodities, and that we're going to see it in the next topic. So what I mean is that in addition to have different processing factor using this same procedure here, but we different, in each case is one different sample, which has a different, because we do that with encouraged residue. We don't fortify the sample, a control sample, to do this kind of thing. You treat the sample in the field, and then you collect the sample and you process the sample. And in the field, you have samples, we saw it, treated and having different levels of the pesticide. So you can have different processing factor for each commodity here. And here is more important, you're going to have very different processing factor for the wet pomace coming from this flow chart here, and the wet pomace come this flow chart here. So that's why you have a wide range of processing factors for the same processed products. Hopefully, we would receive many processing factors that we could make the best estimate of would be that processing factor. Sometimes that doesn't happen. Sometimes we would have 2-3 studies only, but we do go ahead and estimate. With 2, you can really not do too much, but with 3 processing factor values, you derive what we call the best estimate of a processing factor. For example, in this table here, you can see for different pesticides and different crops, you can see pyrimicarp, for example, tomato was submitted to a processing and the final processed commodities juice. And here you see the processing factor. Ideally, actually, you won't expect any processing factor for the production of juice coming for the production of juice. But in this case, we do have a 1.54 processing factor, which is higher than 1. In most cases, juice has a processing factor lower than 1. In this case, we have 4 values lower than 1, which is most expected, but we do have 1 value that is higher than 1. What do we do with this number? So there is one thing when you evaluate any data, not only for pesticide, when you generate data in the laboratory, you look for outliers. Yes, because those outliers are those numbers that are completely out of expected range, or out of the range that was found that you have it. So you have a number that is completely out of that range. This is an issue that we have been discussing even with residue trials for many years, because sometimes the residue trials, it's an important issue. That's why I want to point out here. Sometimes in residue trials, you see that large variation of residue trials. It's normal. But then let's say you have values from 0.05 up to 2. And then you have one other value, which is 10, completely out of space. In many cases, the company may, in some cases, the company may ask you to consider that value as an outlier. But we only consider a value as an outlier if there is a justification for that. So you go to the study and see if there was something weird in the study that you should disregard that trial. So this result here came from a trial, a processing factor, not a trial in the restrict sense of the word as we've seen here, but it's a different study. This is a different study which gave a processing factor. So in this case, we went to the original study. So coming back to the residue trials, we only disregard a number if it's too low or if it's too high compared with the other ones, if there is a clear indication that there was something wrong with this trial. Otherwise, we have to consider it. So we had already in the past many arguments in the company because a higher lab would lead to a higher residue, maximum residue, a higher STMR, and the company may, if the compound would have an intake problem, for example, the company may want that number to be disregarded. The other way is the same. If you have a very low number, maybe the estimation of the maximum residue level will be, now in this case, yeah, the concern is more when you have higher level. So in this case, although it's weird to have juice with a higher processing factor than 1.54, we went to the original study and we found nothing that would lead us to disregard that number. So we just consider it, and what we normally find, it's not to estimate the mean, but the median, which we call it the best estimate. It's like the STMR. Is the median of the value, not the mean of the value. Just because of the large variability, the median reflects better that population. The same thing here. It's not the mean of those values, but the mean that reflect. And when you use the median, the impact of this 154 actually is decreased. Yes, so if you disregard that number here, you take the mean out of those two values, which would not be so different than 0.7. So that's why normally you use the median, not the mean. And here you have other examples for the same study. So a puree was obtained. So the median is expected that puree has a processing factor higher than 1, but in some cases was lower. And when you take the median, it's higher. So when you take the median here, it really reflects what you would expect. And then for another compound, for grape raising, so you really would expect a processing factor higher than 1. And look here. Here it's very weird because you have 0.36, you just have 2 studies, 0.36 and 3.2. So the meeting decides, and that's what I mean. The meeting, it's a group of people, and each decision, it's only taken in if everybody agrees. In this case, the group, because we have very few trials here, the group decided not to consider this one, 0.36, because the residues in raising are not expected to decrease that much. So only the highest value was taken. And then you have thiamethoxam, coffee beans. That's how the coffee is traded. In most cases, green coffee. And here you have roasted coffee, and the processing factor here, it's really very, very low. It's even below 0.14. Because when you have the residue in the processed commodity lower than the LOQ, so will generate a processing factor lower than the LOQ. What you cannot have, you know that for your basic math, you cannot have a value here below in the raw commodity. So you look for, when you conduct the processing studies, that you will have residues in the raw commodity. That's what you're looking for. You may not find any residue in the processed commodity. That's what was the case for roasted coffee. But you may you have to find residues in the raw commodity. That's why in most cases, the company run a separate trial to prepare samples for processing studies. And normally this trial has a much higher application rate than the gap. And it doesn't matter actually, because there you really want to generate a sample with encouraged residue that have quantifiable residue. Because when you will process it, and many of the processing procedures will lead to a decrease of the residue, you need it, the residue will decrease. So you cannot estimate a processing factor when you don't have any residue in the raw commodity. In this case specifically, you did have residue in the raw commodity, but you did not have any residue in the raw commodity, in the processed commodity. That's why we put this value here as below 0.14. But when we apply this processing factor to estimate the STMR, for example, of course, we don't use we just use the 0.14 number, of course, because we cannot consider, but this is an indication that actually the residue will really decrease a lot in the roasted coffee. Just a practical example for grapes producing raisin juice and wine. Normally, the processing studies try to use what would be a commercial processing procedure. Obviously, they will take that commercial practice for raisin production, juice production, and wine production in the laboratory, but try to really reflect what is happening in commercial practice. So here, for example, you have this compound, the STMR is 0.30, and the MRL is 3 milligram per kilogram. And I have to say that when this will be important for the next topic, the dietary risk assessment, for most processing commodities, you will not estimate an HR. Why? Because an HR, normally the processed commodity will be a blended in the field, for example, to produce juice. It takes the juice, the grapes from many fields to make juice. Wine is the same. So it doesn't come from the same lots. So you blend it. So that's why there in the acute dietary intake, you won't use the HR. You're always going to use for processed commodity, the STMR. In some specific case, you use the HR, but in most cases, you use the STMR. So for raising, the processing factor was estimated as being 2.6. For juice, a huge decrease in the residues during juice production, and wine 0.06. So the STMR-P for each one of those values is the STMR for grape multiplied by the processing factor for raisin, and then you have the STMR for raisin. This is very important because imagine if you have an STMR, in this case, you really increase the residues in raisin mainly because the raisin during the raisin production you lose water. So here you really need a processing factor to really reflect the residue in the raisin. For juice, if you did not have a processing, yes, Someone
E aí, o que eu vou fazer? Fazer um omelete, né?
Can someone mute someone, some Brazilian who is talking about lunch? For juice, if you did not have that processing factor for juice production, you have to use in the dietary intake estimation, chronic and acute, the value of 0.3. Although there is a reduction during juice production, and the STMR that you put there in the calculation is 0.002, much lower. For wine, 0.2. And from all those processed commodities, the only one which deserves an estimation of maximum residue level limit, an MRL, is raisin. So you just multiply the processing factor for the raisin, 2.6 times the MRL for grapes. So you have a number of 7.6. So you round up, and then you recommend an MRL of 8 milligram per kilogram. So, so that's it. You're going to see some processing commodities when we talk in the next topic. So, and finally, within this chapter, I think it was not in the program, but I think it's important for you to know how national governments and the GMPR derive maximum residue levels, STMR, and HRs for animal commodities, meat, eggs, milk, edible offal. So it's a much more complex procedure. I will try to explain very slowly. It's not trivial, but let's see, because here in Brazil, we don't have this procedure. I don't think maybe people from Argentina can tell me if you do have this procedure, if you derive your own MILs for animal commodities. Here in Brazil, this procedure is not has not been taken by Anvisa, as far as I know. And actually, the Ministry of Agriculture, who deals more with animal commodities, takes up the Codex recommendation. But here, how it's done. You need the residues in the feed, the median or the highest residue in the feed. What is feed? Feed is alfalfa, for example, is feed, any grass, any rest of the plant of the grains, for example, wheat. You harvest the grain and there is the whole plant that is left. So, and then you may feed the forage to the cattle. You may feed the dry material to the cattle. Everything except the grain goes to the cattle, but also you can feed the grain to the cattle as well. When, for example, when the grain is not of very good quality, you just give it to the cattle, to the animals. Maize, for example, you know, it's a major feed for poultry. Yes, here in Brazil, at least, a big part of the maize production go to poultry consumption. It doesn't go to the food industry, but goes to the poultry industry because it's fed to the poultry. So you need to know, of course, the residues, pesticide residues in feed, in any feed that is provided to poultry. Actually, we do it for mammalia. That could be normally cow or goat, and poultry. Yes, and then we have recommendation for these two groups of farm animals. And then you have what we call the OECD feed table. I'm going to show you later what is the OECD feed table. It's basically our food consumption table. for humans. So there is a feed consumption table for farm animals. And that feed consumption table was put together by the OECD. And then, so the procedure is basically what we do for humans. You multiply the residues in the feed times the consumption of each cattle in the feed consumption table. And then you calculate for humans, you're going to see more closely, you calculate the human intake of that pesticide through the consumption of food. Here we calculate what we mention as dietary burden for animals. It's basically the same thing. You multiply the residues in the feed by the consumption of that feed by the farm animal, and then you calculate the dietary burden. And then, so for humans, you stop there, you calculate the dietary intake, and then you go further to the dietary risk assessment. For animal commodities, you have that value and compare what we call feeding studies. So the feeding studies is different from the metabolism studies, because the metabolism study is done with label compounds and everything. Here, feeding studies, the company does that. Give to the animal a dose of the pesticide that would be close to the dietary burden. And then they kill the animal after a certain time, normally 28 days, give that dose to the animal normally every day. At the end of 14 days, 28 days, kills the animal, collect many things, collect feces, urine, and blood, gastric contents. But what is most important for us are the animal foods that are relevant to human consumption. So they kill the animal after a period of time where the animal was exposed to that pesticide at levels that approximate the dietary burden, analyze it. That's why we need analytical methods, validated analytical methods for animal commodities. So for meat, for edible offal, liver and kidney, and for milk and for eggs. Remember, back there, we talk about it. For example, for metalaxyl, we could not estimate the STMR, HR, and MRL because there were no validated method for animal commodities, period. We cannot do that for plants and for animal commodities as well. So, and based on what is found in these animal commodities from the feeding studies, which was conducted, approximate the dietary burden. If not, we apply approach similar to the proportionality. We estimate STMR, HR, and MRLs. So that's the whole procedure. It's a bit more complicated. Here is some examples for feed. For example, what the animals can eat. Here in Brazil, because the cows in Brazil, we have extensive agriculture. What I meant, I don't know exactly the terms, but our cows here in Brazil, and I think in Argentina as well, in most of Australia, in the US, the cows are actually, they eat feed, but they go to the open air to eat the grass in many cases. So normally, cabbage heads, kale leaves are not important components of the Brazilian cows. I'm not sure. Maybe there is someone from the Ministry of Agriculture there. I'm not a farm person at all. And I cannot tell because in the OECD feed table, Brasilia, the farm animals diets is not are not included there. So I don't know anything about what the Brazilian farm animals consume. I know that the poultry consume a lot of maize. This is for everywhere. And then, so they can eat these vegetables, which are very important in Europe. They can eat, of course, grain stalks, forage, straw, and the grain itself, potato coals, cotton, underlined seed. And here are the HRs, the STMRs, and they can also consume processed commodities, such as cotton hulls, cotton meal, and rape meal. And here are the STMRs. So as we have HR and STMRs to conduct the dietary intake assessment for humans, we need the HR and STMR to calculate the dietary burden for the farm animals. Here, yeah, we need those numbers to calculate here. And in addition to the residues, we need the OECD, the diet for the animals. And here I'm gonna show you how the diets for these animals look like. So I hope it's open here. Very quickly, we're not going to do any exercise, but I really want to show you how it looks like for those of you who never seen this, are not very interested in minor, are not very interested in animal commodities, but I think it's important. First, I have to open here in my computer, sorry. I had it open yesterday. I don't know why it's not open here. Wait. Oops. Here. I knew I had it open. So I want to share with you this OECD fit table. I don't see it here, but I open it here. Here's the fit table. Before, we used to really make all those calculations by ourselves, but then someone from Christian from BFR just put together this template. It's just a macro, just we have similar to what we have for dietary human exposure. So here we have all the feed that the farm animals could eat, the group, the codex group, and the feed itself, the crops. And we have the codes, and then we have a place to put the HR or the STMR. And here it really tells you which one you should use. Here it applies for some crops a dry matter content, because for crops actually who eat the dry feed. And then you have here the feed consumption information. And this OECD feed calculator has consumption for farm consumption data for farm animals in US, in Europe, in Australia, and in Japan. It doesn't have here, I keep complaining here in Brazil that it should have here the Brazilian consumption data for farm animals, because Brasilia is a major, in Argentina as well, it's a major cattle meat export. So we should have, Japan does not export cattle meat. It's a good important, but it produced very few, but the diet from Japan is there. And here there is a difference between beef cattle, dairy cattle, cattle who are for milk production, and here has also for sheep, lamb, but normally we don't have information for those farm animals. Swine, and then you have poultry, and then you have broiler and layer poultry. And then there is a consumption, for example, here for layer poultry, basically we have consumption for some crops only in Europe, yeah. And then you can go down, and here you see for layer, basically data from Europe. But the calculator just do make the estimation with the data that you provide there. And then you have a summary sheet. Actually, we have very few things numbered there. Actually, this was the table for metalaxyl, I think. So it just comes out only for the feed that you enter a number. And then it summarizes here the data for US, for beef cattle, the data for to estimate the maximum residue level, to estimate the mean STMRs, and then you just take the highest value here. So you see here for consuming cabbage heads and potato coals, you own the highest, the most critical diet was from Europe, and then it estimates the dietary burden. And here for maximum residue level, and here also for the mean residue level to estimate the STMR. So basically that's what it is. I just want to show you. And then we go back to the presentation. It generates a table like that. And then here's just a summary table, where you have the dietary burden for beef cattle, dairy cattle, hens, poultry, broiler, poultry, layer poultry. These are the values to estimate the maximum residue levels, and those are the values to estimate the median residues. Here the maximum residue and the highest residue, and here the median residues, here the median residue. And here below, it tells you that for beef cattle, you should choose the highest dietary burden, which came from Australia. So that's what you're going to use to estimate the maximum residue level and the HR for mammalian, meat, fat, and edible offal. That's the dietary burden that you're going to use it. And here, it's 22.2. The data comes also from Australia. You're going to estimate the MRL for milk because it comes from the dairy cattle. And here's the same rationale for poultry, the highest residue and the maximum residue level for poultry, commodities, and the means for estimating the STMRs for beef, for milk, and for poultry. So that's just a summary table. And what we do, so we do have now the dietary burden from all animals based on the consumption of feed by the farm animals and the residues, pesticide residues found in that feed. So we have the dietary burden. But then we need the feeding studies. So normally the company makes that exercise and estimate a dietary burden. So the company knows that the feeding studies, they have to conduct around those levels. Yeah. And here we have an example where actually they conduct in various levels, but also conducted at the level which is the highest here, around that level. And for here's for this is I'm just showing only for cattle, okay? And the company then gave daily dose to the cow of that milligram per kilogram body weight in the feed, gave it to the cow, and then at this level, did not find any residue. At this level, higher level a little bit, found some residue. This is the highest value, and those are the individual values for the, no, this is not the highest. Yes, this is the median value here in the top, and these are the individual values for each cow. Normally, for big animals such as cow, they use normally 3 animals only. So each value entre parentheses correspond to the liver of one animal, other animal, other animal. Here's the same. And you see that the highest dietary burden, which is pretty much close to the highest dietary burden here, a lot of residues were found in liver, kidney. Normally, that's where you have highest residue. That's why the MRLs for edible offal and the STMRs and HRs for edible offal are the highest, because we know that's the liver is where all cyanobiotics are metabolized, and liver, it's during the excretion of those compounds and their metabolites. Muscle, very low, half, and fat. So that's what we want to know. And then the next step is just to put those things together. You have the feeding study, you have the dietary burden, so you just make a proportionality here. And then you're going to have, in these cases, for dietary, here you have the total flunicamide, which is for the residue definition. And here you have for maximum residue level, here for STMR estimation, and then you find actually the final residue at the dietary burden that you would use to estimate an STMR and an HR. So it's a bit complicated, but I'd like really to show you in a general way how that works. And with that, we finish chapter section 4, and I'm open for questions.
No veo preguntas en el chat, pero creo que Adriana tiene la mano levantada.
I have a question. Yes. Thank you.
Oh, Jason?
Yes.
Jason, in my watch here is 12:20.
Oh, it is time. Perfect. Yes, I'm sorry. Yes,
so
we
maybe
do.
It's a
I
good
lost
time
track
to
of
have
time.
a break. Yes.
My apologies. Yes, that is correct. It is
Perfect
time
time
for
to
break.
have a break, and then we can initiate the next topic. It's perfect.
Correct. Okay, thank you. We'll go for our 10-minute break now, and we'll resume in 10 minutes. Thank you.
Okay. See you later.
Nos encontramos en las instalaciones del ensayo 12318-19 S01, que corresponde al ensayo de determinación de residuos de la combinación espinetorampiña. Nos encontramos con Germán Lochamín, que es el director ejecutivo de Asopiña, y el gerente general de Agroeden, que es la empresa donde estamos haciendo los ensayos.
Productores formales en el país, para llamarse exportadores deben cumplir con sistemas de gestión, certificaciones que avalen un producto inocuo. Las certificaciones, estamos hablando de buenas prácticas agrícolas o Global Gap, que es el requerimiento mínimo para poder exportar. Todas nos exigen el cumplimiento de directrices con respecto a LMRs y a listas de productos que podemos usar. Partiendo de eso, podemos decir que el cumplimiento de los LMRs establecidos en países destino es uno de los principales retos. ¿El por qué? Porque, como ustedes sabrán, hay muchas moléculas a las cuales sus LMRs se están reduciendo y muchas otras que dejan de estar autorizadas para su uso, y eso nos reduce a nosotros como como productores de cultivos menores, nos reduce la posibilidad de tener moléculas y así evitar resistencia de plagas y enfermedades. Entonces, son muy importantes. Nosotros no tenemos otros medios por los cuales podamos primero permitir que cultivos como la piña en este caso tengan su interpretación de nuevas moléculas. Para nosotros ha sido muy complejo entrar a algunos mercados en los cuales no hay nuevas moléculas, y que en otros mercados con mucha más investigación, hablamos de Europa, Estados Unidos, de moléculas donde ya se permiten, ya se manejan, pero nosotros no podemos enviar o mantener nuevas moléculas porque en sí el producto no está ampliado para piña. Los LMRs no existen, entonces eso se vuelve muy complejo y nos ralentiza el avance que como sector productivo necesitamos, ¿no? Que es algo muy dinámico. Salen moléculas, tenemos resistencia de plagas, tenemos que siempre estar innovando y buscando evitar la resistencia de plagas. Entonces, el tema de que la fundación apoye con estas investigaciones son muy relevantes, ¿no? Sí, es importante no solo apoyar desde nuestra parte productiva, sino procurar que esto se profundice y lo hagamos mucho más. La limitación de uso de moléculas, por así decirlo, medianamente antiguas, nos ha limitado mucho, y hay que tomar en cuenta que todo lo que son cambios climáticos, ahora mismo aquí en el país tenemos mucha variación de clima, no podemos definir, ya no tenemos definidos nuestros veranos, nuestros inviernos, tenemos poblaciones flotantes de plagas que son estacionarias, que tienen un comportamiento errático para lo que nosotros manejábamos, y eso va a involucrar retos muy importantes ligados al tema de desarrollo, investigación, uso de nuevas moléculas, y por ende es muy importante el trabajar mancomunadamente con todas las organizaciones para poder establecer estos LMRs y poder usarlos en nuestros cultivos.
Sí, ya estamos de vuelta.
Yes, we would like to see if Eloisa is ready to continue with the next session.
Hello, yes.
Hello, welcome back.
Let's start then. Where is it? Here. Okay, let's then start our last section of the workshop, which is estimation of dietary intake and risk assessment. So first of all, we're going to start with some principle of dietary risk assessment, talk about chronic intake, and I want to show you the IEDI spreadsheet, acute intake, IESTI spreadsheet. Oh, let me correct this, otherwise I forget. And then we'll give some examples. And also, I want to show that I think everybody's curious about it, how this process can impact the MRL setting by the Codex Alimentarius Commission. So I don't know how much familiar you are with the risk analysis paradigm and the components of the risk assessment. So this is the risk analysis paradigm. Many people, at least here in Brazil, get confused about the words risk analysis and risk assessment. So those are two different things. Risk analysis includes the three components: risk assessment, risk management, and risk communication. In the FAO, WHO, CCPR system, or Codex Alimentarius system, because actually this applies not only for the CCPR committee, but also for the other committees in the Codex system, such as JECFA, for example, which is responsible for food additives, contaminants, and veterinary drugs, and CCPR for pesticide residues. And then we have the scientific part, which is what I do and which is what I like, and that's what GMPR does. The GMPR review, evaluate all the data that we've been talking about here in these 4 days to get to the final question, and which is the human exposure to this pesticide, in this case of the GMPR, through the diet is safe? Does that bring any health concern? That's the GMPR final question that we pose to ourselves, and that's the answer that we are looking for. And we need to go through the whole process before we can answer that question. And then we pass the information. In the case is the MRL's recommendation. Again, we first estimate, then we recommend and send it to the CCPR. And the CCPR, as a manager within this risk analysis process, make the decision. At national level, for example, at national level, who makes the decision depends on the government structure. In Brazil, for example, Anvisa does everything as far as MRL setting and management decision regarding that. It's Anvisa who does the risk assessment, the dietary risk assessment, and Anvisa established MRL, which is the regulatory and the management decision here. At international level, that role is CCPR role. CCPR does not regulate anything. actually everything that we do at GMPR is passed through CCPR. CCPR adopt as a codex standard, but we cannot enforce anything. We cannot, it's a guideline, it's standard, codex standard, but it's up to the government really to decide if they will internalize that decision or not. Use that the decision. You know that after the trade agreement many years ago, the codex standard should be accepted in trade relationships. So, but we know unless there is an indication that there is a concern for consumer health, although it's not always like that. Sometimes we have barriers in the international trade that are not justified by the potential health. They are just barriers because sometimes even because it should be clear actually to everybody that the fact that a compound has a residue level higher than the MRL does not necessarily indicate a health concern. And some people, even at international level, use the MRL as a trade barrier, but it should not be, only if that level found in the sample indicate, in the food indicate a health concern. But we all know that life is not fair at all. And although the Codex would like to promote fair trade, in real life, that's not what happened. And many in each country, people who sometimes really are laboratory people who are really involved in the daily routine only to analyze residue, and sometimes even these people are not aware that a sample that contains residue higher than MRL does not necessarily does not necessarily indicate a risk. And that's why we need dietary risk assessment. There are some issues about that. Some countries, mainly in Europe, are kind of stepping away a little bit regarding the risk assessment principles. But I hope Brazil doesn't do it. I know that US doesn't do it, but Europe has a very conservative approach, and for some pesticide, they are going away from the risk assessment principle. So the risk analysis then is the risk assessment, and that's what we are talking about here. But we will also talk about how the result of the risk assessment affect the risk management decision at CCPR. Risk communication should permeate everybody, the risk assessors and the risk management. And we do have a very good communication. I mean, the GMPR group have a very good communication with CCPR. Many people goes to go to the GMPR, and also they go to CCPR as a member of the country delegation. But actually, again, at GMPR, they have a role. At CCPR, they have a completely different role because there they are representing the government, and they are the role of managing. But there's risk communication. I show you some examples where actually some procedures that we do at GMPR were suggested by the risk manager, and we consider it scientifically if that was adequate, and we did apply some of those. For me, like the alternative gap, it's really should be kept at the risk management level, but it was decided by the risk assessors, which is the GMPR, to take that in our common procedure. So this was my personal opinion separately. So there is a big communication between the GMPR and CCPR. And actually some years ago, a chapter was included in the report only to deal with the CCPR questions which are raised during the meeting to be answered by the GMPR. So before, maybe that chapter was included, it was actually suggested to be included maybe 6-8 years ago, maybe more. And now it's chapter 3. If you go to the report, you see that chapter 3 is answers to CCPR questions. And chapter 4 is the dietary risk assessment. But this was included, this chapter, only to facilitate the communication and the transparency between GMPR and the CCPR, between the risk assessor and the risk manager. Because during the CCPR meeting, many of you have attended at least one meeting of those. The delegations ask questions. We normally get a lot of questions from the EU delegation, who questions some of our procedures, even for the they send questions for the WHO group and the FAO group, and sometimes they do find some errors in our evaluation or in our report, and we are glad to that they do that, because then we have a chance to correct it, and sometimes they only question our procedure or only question our approach and our decision, and we have to answer point by point. So that's chapter 3. And that's part of the communication between the manager and the assessor. And there is a big issue nowadays, communication with the public. Yes, you who work at the government, Anvisa here has a huge task of communicating the Anvisa's decision to the people, to the media, and to the people in the media is a good way through reach the general population. So this risk communication issue is a key issue. Europe actually have been taking some approach because sometimes they find it easier to be more conservative in their approach, because really to communicate that to the general public sometimes is very difficult. And we're going to see it later in the equation that is used for acute intake. And so that's really challenging to make a good communication. Again, pesticides, actually, there is no pesticide that really, there are epidemiological studies that prove pesticide can cause cancer, at least pesticides which are that we are exposed to the diet. Occupational exposure is something else. We are talking here about dietary exposure. But we have a lot of compounds that we expose, chemicals that are exposed daily in food, for example, mycotoxins. Aflatoxin is genotoxic. There are many studies, it's really classified as a human carcinogen, but most people do not even know what mycotoxin is. And it's a natural compound that contaminates food because it's produced by fungi. So people are not concerned about it because mycotoxin is a natural compound, but pesticide is produced by humans. There are a lot of companies involved in pesticide production, so people are really scary about pesticides. And it's a challenge for the government to do a good communication that if they eat a good plate of salad, they will not die. Yeah. So it's always a challenge. So in this presentation, focus on the risk assessment part, the scientific part of the risk analysis, and we will, as I mentioned, to give some examples on how the result of the risk assessment will impact the CCPR decision as a risk manager. And I want to point out that in Europe, those roles are very separated, because who does the risk assessment for pesticide and many other compounds in food is EFSA, but the decision, the management decision, is taken by the EC, the European Commission in Brussels. Yes, and some countries also these roles is very defined. In the Netherlands, for example, the risk assessors is one, even they divide the city. The risk assessors are in one city and the risk manager is in the different cities, although they are not the same person who conduct the risk assessment and make the decision as risk manager. Here in Brazil is everything in Anvisa, everything in one body. Actually, the people who does risk assessment are the same people who does risk management decision. So at least within one single institution, yeah. Although the risk management decision are done at the higher level or within the organization, but it's within the same organization. And in many countries, they have changed that, and you have different organizations to deal with risk assessment and risk management. After saying this, this actually slide shows the same thing as I said before, but even only in a more detailed way. So again, the GMPR recommend MRL, SMR and HR, establish ADI, and conduct the risk assessment. The CCPR accept our recommendation, and then the recommendation are adopted at the CAC. This whole process since 2007 is being very accelerated. For those of you who knows the Codex Alimentary steps, it goes from 1 to 8, and 8 is really the adoption of the Codex MRL. And normally before 2007, in 2007, there was a CCPR meeting here in Brazil, and it was in that meeting, and I was present, by the way, that it was decided to accelerate this process. Because before, we always had the GMPR meeting in September, always, and before in September of year 1, for example, and the decision by the CAC would only be taken at year 3. So it would take 2 years for our recommendations to go to the Codex Alimentarius process steps. So it go to step 1, 2, 3, 4, 5, 6, 7, and 8. And since 2007, we have an accelerated process which goes to step 5 to 8 in one single meeting. So we have the meeting in September, always, and then we publish the report first and the evaluation. Normally the evaluation will be available in February the next year. And then in the next year, in March, April, there is a meeting in the CCPR meeting, and the decision by the CCPR are sent to the CAC, which is the Codex Alimentarius Commission, which is the final manager. And the recommendations that we did in September in the previous year will be Codex MRLs in the next June. So that is the accelerated process, where the step 5 goes directly to step 8 without passing through step 6 and 7. So this is very fast. It's as fast as it could be. Here is September, 1 year. Here is already in June of next year. And how is the dietary risk assessment process? The dietary risk assessment has 2 major components. The toxicity component, and at GMPR, it's and the toxicity component is composed by 2 steps: the hazard identification and the hazard characterization. In most cases, and these steps will lead, actually the hazard characterization step will lead to the estimation of the acceptable daily intake, the ADI, and the acute reference dose, the ARFD. In most cases, they studies the decisions or the derivatization of the ADI and the acute reference dose is done based on the laboratory studies. There were in the past some human studies, but ethically they are not conducted anymore. So basically we have laboratory studies, in most cases rodent studies, rats and mice. And this work here is done by WHO panel. But again, we have close communication with them. And this is the toxicity part of the dietary risk assessment process. The second part is the exposure estimation by calculating the intake. And the intake for dietary exposure is done basically by knowing the food consumption by body weight times the pesticide residue. That's why only knowing one part of this equation, we're not going to say anything about safety, because to tell you about safety, you need to know the pesticide residue level, for us are the HR and the STMR, and the food consumption with the body weight. And to really answer the question, is the exposure safe? We need the numbers, the hazard characterization number, which are the ADI and the risk assessment, to answer the question and to go to the final step of the dietary risk assessment, which is the risk characterization. To answer the question, is exposure safe? So when we finally can answer that question, our work at GMPR, it's kind of done. So that's why, although we for us in the FAO panel, we start doing the dietary risk assessment back home, as I'll show you, but we really finalize all the numbers during the meeting. And normally in the last week of the meeting, actually, because sometimes in the last 2 days of the meeting, the WHO panel are still discussing about which number should be the ADI, which number should be the acute reference dose, if a compound should have an acute reference dose or not. Because some compounds, all the compounds should have an ADI, which is the safe exposure level for chronic exposure, but not all the compounds have or need acute reference dose. So for compounds that are of very low acute toxicity, maybe the meeting should decide that an acute reference dose is not necessary. So in that case, we don't perform an acute dietary risk assessment, but only a chronic dietary risk assessment. And we don't go forward with our recommendation if we don't conduct a dietary risk assessment. It's just, if there is no ADI, I remember that, again, I have to talk about my metalaxyl. Metalaxyl was supposed to be finalized in 2018. But why it was not done so? Because I had done my work in the FAO part, but WHO needed additional data to establish an ADI and acute reference dose. So in 2018, it was decided that we could not finalize metalaxyl M because there was no decision regarding the ADI and the acute reference dose. And without that, I cannot do the risk characterization, although I could do this part and finalize the dietary risk assessment. So 2018 it was not finalized. 2019 not yet, because the company had not provided to WHO the data that was necessary. 2020, there was no meeting, even remote meeting. And then we finalized metalaxyl-M in 2021, because then we could do it. And we say that risk may exist if the intake estimate by the food consumption data that we have available and the pesticide residues, that means STMR and HR, is risk may exist if this intake here is higher than the ADI and or the acute reference dose. If it's lower, there is no health concern for the human population. I think I have part of this in Spanish or even in Portuguese, but in Gestão it's intake, sorry. I'll change that later on. So this is the whole issue. We'll talk a little bit about this toxicity part, just for you to know how these numbers are derived. Just very short, one slide, because I do conduct studies on rats as well in my laboratory, not for pesticide, but for plant extracts. So most of the studies are conducted in rat. They are conducted by the company responsible for the pesticide, or the company that is provided the data package for the toxicology part, and it's provided to the WHO group. In most national governments, you also have a group of experts for the residue part and a group of experts for the toxicological part. So the company provides many laboratory studies, and based on the most critical study, in some case, and each study may derive many response curves like that, and may derive many low ILs and no ILs. What is a low IL? Low IL is, I think I don't have the box here with the definition. Low IL is the lowest observed level which have adverse effect level. For example, in this study here, lower observed adverse effect level. In this study here, this level here led to a response. And of course, we are looking for adverse response. But what we are really looking at is the level in the rat that did not cause any adverse effect. So the no IL is the no observed adverse effect level. That's the number that we are looking for in a laboratory study, rat study, or maybe sometimes even dog studies. They use dogs to conduct. Sometimes we derive a no IL from studies conducted in rabbits, in dogs, but in most cases are rodents, mouse or mice, rats or mice. And this no IL coming from the rat studies indicates the level, the dose to which the animal was exposed to, that caused no adverse effect compared with the controls. We always, in a experimental study, we have a group of control rats. That means that group, which has 20 animals sometimes, they were not exposed to the compound, in this case, to the pesticide that we are investigating. And then we have 3 or 4 other groups, or 2, 3 or 4 other groups, which are exposed at different doses. And what we are looking for at the dose that the rats were exposed, which did not cause any adverse effect compared to the control. And that's what we call a non-observed adverse effect level, known as NOAEL. But this is in the rat. We are looking for, this is safe exposure level to the rat. But we use these studies to derive a safe exposure level to humans. And we assume that we humans are 10 times more sensitive to than the rats. That's an assumption, a conservative assumption, because sometimes the rats are more sensitive than we are. But this is a conservative assumption. We are more sensitive to the rats. So if a dose level of 10 milligram per kilogram body weight was safe to the rat, that means that the safe dose to you, to the human species, 1. That means 10 times lower than the dose that was found to be safe to the rats. But we humans are not the same. There is a variability within the human population. That's the same as there is a variability within the rat population. But this rat population, normally they are very comparable genetically, and they are isogenic. It's an isogenic group, although there is certain variability, but it's much lower. So we have to take into account the variability of sensibility within the human species. So when we apply a factor of 10 to the safe level of the rat, so we find that 1 milligram per kilogram per body weight is safe to the mean, to the average population. So here, these people, they have a average sensibility. They don't have any serious disease. They don't have any hepatic problems, renal problem. They are not children. They are adults. They are not elderly people. So this is just the average population. But then you have to take into account that within the human population, you have people that are very sensitive for one reason or the other. Children, older people, people who have some disease. So to that level of 10, we apply first an uncertainty factor of 10. And then we found a safe dose to the general population, but then we applied another safety factor of another 10 to protect the most sensitive subpopulation within a human population. So the safe dose to the rat is 10, and the safe dose to the human population, to the most sensitive subpopulation of the human population, is 0.1. And that's the ADI, or the acute reference dose, because the acute reference dose is derived in the same way. So that's how we go from the rat study to find a safe dose level to the rats and to arrive to a safe dose level to humans, which is the ADI or the acute reference dose. And this kind of slide here just summarizes what I said. Yes, the different species, rat, human, and the human variability. Yes, and these numbers 10, they are easy because you just divide by 100, just move the common. But those numbers were derived from many studies, actually, which takes into account the toxicokinetic and toxicodynamic within each species. So that's an old number that has been going around. So kind of start in the 70s, the 80s, where the risk assessment paradigm was really put together by the US government, US institutions there. It was 1984. In Brazil, this concept arrived 20 years later, but anyway, the principle started to be really systematized and underlined in 1984. So that's how we derive the ADI in acute reference dose. And then that's how I'm going to talk about the WHO group work, because we're going to need those numbers. And that what is really concerned to us that is dealing with the residue of the pesticide in the food. And then we do have to also be concerned about food consumption and the body weight. When you look at that equation, you see that to estimate the intake, the residue concentration has the same weight in the equation as the food consumption and the body weight. So it was when I started working with the dietary intake assessment, just to realize that it doesn't matter if you have, here in the laboratory, I have a very nice laboratory, by the way. We have 2 LCMS MS, 1 GCMS MS, and another GC FPD CD. We have HPLC. I have a very nice laboratory here. Our methods are accredited. I have people who work here. But it doesn't matter if I have a very nice laboratory to generate a very good and very good residue level if I don't have good food consumption data. Because if I have a good concentration data, but a bad consumption data and a bad estimation of the food consumption by a population and a bad estimation of the body weight of that population, the intake calculation will be bad. And the whole dietary risk assessment will not be good as well. So we are laboratory person. We are concerned about the good laboratory data, but we should also be concerned about a good consumption data to conduct exposure assessment. In the exposure assessment, you need to estimate the exposure for chronic exposure and for acute exposure. For chronic exposure, it's normally a lifetime exposure. Yeah, since you are a child until you are done with the life in this planet. And normally we assume that the exposure will be an average exposure, because one day you eat a lot this food, and this food has an average residue concentration. The other day you eat less, and you go like that, yeah, in your time life. Sometimes you are highly exposure and then not too much. So you have along your whole life periods of high exposure, low exposure, or so you stay in the average to really estimate. That's why the ADI, which are estimated here, the rats, to estimate an ADI, they are exposed through, normally the ADI are derived from rat studies which were exposed during 2 years, which is kind of a lifespan of rat. So the chronic exposure actually should reflect the average exposure. Let's put the other way around. The average exposure and normally the usual food consumption of the population should reflect the chronic exposure throughout the life. So we use the average pesticide level, which for us would be the median level of the residue trials, the STMR, and we use the ADI for risk exposure. We use it depends, the mean consumption level. It's an exposure that occurs daily. It's like the rat, which is exposed daily to a certain substance throughout the whole lifespan of a rat. And the studies are about 2 years, most of the studies which the ADI are derived from. What about acute exposure? Acute exposure, it's, you know, that day that you decide to make women normally they have that. I want to do a diet based on only apple. Maybe I can lose 3 kilos in one day if I eat only apple today. That should not happen every day. You eat a large amount of apple. And by chance, you were not very lucky that day. You went to the drugstore, to the supermarket, and you were not very lucky because the apples that you bought there came from a lot where the residues in that lot were very close to the MRL, were higher residues, were the highest residues. So the apple that you consumed, that you bought, you brought to your house, had the highest residues from that lot, and you decide to consume a lot of apple. So you have high concentration level and high food consumption level. And this occurs sporadically, hopefully. You'll not be consuming a high amount of apple every day in your life. You are really hopefully you are really consuming that sporadically. And the acute reference dose also reflects that an exposure that occurs during a short time of period, normally 24 hours. So the acute exposure, it's that peak on your life where you are exposed to a high levels, your intake is very high, but occurs during up to 24 hours. So normally you can in only one meal or during 3 or 4 meals during that day. So while chronic exposure during a long period of time, acute exposure is supposed to be during one day. And I may say already to you that a third kind of exposure is being discussed at GMPR. These are shortened, it's called shorter than lifetime exposure. And this actually wants to mimetize not a long-term exposure, neither an acute exposure through 24 hours. It's mostly what a children, for example, would be exposed through that short period of time when you are a child. Yeah, everybody was a child at some point. So it's not, because here chronic exposure comes from all the lifespan of a human species. Acute exposure during one day. And here this less than lifetime exposure is supposed to reflect a shorter period than a life exposure, but higher period than 24 hours. So if you see the report for this year, actually you could see that less than lifetime exposure already from the report of 2019. I think 2018, we start talking about it already, but it was not finalized. There is a model that is used to do that. And it's a completely different consumption data package, consumption data. And in 2018, there was an introduction of that issue in 2018, 2019, also an introduction, but it wasn't until this year, 2021, that the procedure was really included in the GMPR procedure. And you could see that in chapter 4. I'm not going to talk about this here. We will stick to the chronic exposure and the acute exposure. But be aware that this third possibility of exposure is now included in the normal procedure of GMPR. And it may affect in the future also the MRL setting. The examples that we saw this year did not have any health concern at all, but may in the future impact the MRL setting. Nowadays, what most impact the MRL setting is really the acute exposure. Very rarely, I had to look for the GMPR reports to find a case. So I found a case to show you where the chronic exposure really show a health issue. But the acute exposure, normally we have an acute problem. And that is what most impact the MRL setting. So let's start with the chronic or long-term exposure. Even the GMPR have going back and forth by using chronic or long-term. And we apply the same question, the same equation that I showed you before. Basically, it's consumption, concentration times consumption divided by body weight. And the chronic exposure at GMPR is called International Estimated Daily Intake. And there is some symbol here that means that we have to consider the intake estimated by the consumption of each crop, food, for which there is an MRL recommendation. So you have an STMR of, and this of course is for each pesticide separately, the STMR of one pesticide times the consumption, the STMR of the pesticide in a crop times the consumption of that crop, plus the STMR of derived for a crop times the consumption of that other crop. So you have a sum of intakes, individual intakes coming from the consumption of individual commodities, and divide by the body weight. Yes, that for the GMPR is only one body weight. You're going to see the consumption data. STMR is the supervised trial median residue. When I started in GMPR in 1997, it was the first time that the STMR was being used to estimate the chronic intake. Before it was the MRL. And for some time we had a mixture of STMR and MRL. It wasn't until maybe 5, 6, 7 years later that we replaced all the MRLs by the STMR, because the old compounds for which there was no STMR derived, we were still using MRLs in this equation. But MRL was long ago gone, and start to be using by the GMPR in 1997. So here STMR we derive from residue trials. You know already how it's derived, but which data we use for consumption data? We use, many of you know already, the 17 cluster diets. Before, when I start, we use the regional diets. And then in 2013, we start using the 13 cluster diets. And now, since 2013, we use the 17 cluster diets. Before then, the regional diet, the 13 cluster diet, and we use now, for a long time already, the 17 cluster diet. This diet was derived from the FAO data that the countries provide to FAO. The country, each country, member country, provide the FAO with data on, say, for each crop, for each commodity, how much they produce, how much they export, how much they waste. So there is a huge data, the FAO data, the FAO has this huge data provided by the countries. Finally, so you have how much it is produced by the country, for example, rice production, how much the rice produce, minus how much rice the country exports, plus how much rice the country imports, minus how much rice the country wastes, because it's crop that is no good for consumption, may give into the cattle, for example. With that FAO data gives in each country how much rice is available in the country to be consumed by the population. And then that number is divided by the number of people who live in that country. But it's not that simple. How these cluster diets were put together? There was a group of statisticians and mathematicians who kind of applied a model to that FAO data and found 17 different patterns of consumption, of food consumption, of all the foods. I like it better, the 13 cluster diets, to tell you the truth, because here in these 17 cluster diets, we in Latin America, we all belong to cluster 5. With the exception of Paraguay and Uruguay. Uruguay, look, belongs to the same cluster as Australia. And I think it's because of the meat consumption of Paraguayan people is similar. Uruguayan, sorry. The meat consumption of Uruguayan people is similar to the meat consumption of Australian people. This data is old already. This cluster diet should be revised. And Uruguay consumption, look at the color. So what means here is that we are here in Latin America, with a few exceptions. You could see an exception here. I don't even know which country is that. You could see some exceptions here. Here is closer. Oh, here is Haiti is more close to here. Some countries in Africa, which is closer, cluster 13. Here, this cluster here, C3, which is Paraguay, it's more closely related to some clusters in Africa as well. And you have this green here, C12, in this country here, in this Caribbean region here. I don't know which country is that, but I'll see the template, because see there you can see all the countries spelled out. In blank is where you have no data. And so here in Latin America, most of us belongs to the same cluster. That means that for dietary risk assessment conducted by GAPR, everybody eats the same. It's similar. And in the past, Africa countries have very few clusters. In the beginning, was only one regional Africa diet, but now you see that Africa has 1, 2, 3, 4, 5, 6, 7, 8, at least 8 different diets in Africa. And here you see India, yes, China, Japan, it's pretty much like China, Indonesia, those Asia countries here. Here you have India, Bangladesh, Russia, who apparently eats the same as US, Canada. And then you have some Nordic countries and UK, here, France, Spain, Portugal, German. So that's the cluster diet. There are 17 cluster diets, and we have to live with that. What I may say that before in the 13 diets, it better reflects the diets from Latin America, but probably not so well the diets from Africa. But this diet, I'm expecting that should be revised soon, because we have been using that for almost 10 years now. So we should revise that. And here we assume that everybody has a body weight, a mean body weight of 60 kilos, with the exception of Asian countries, who for which a lower body weight is considered, because they say, no, we are smaller, we weigh less than everybody else. But we basically have 2 body weights for that equation there. So with that, I don't know if we want, maybe I should already show here and then we go to the Qt tomorrow. I'll share with you before we go to questions, the ADI, the chronic intake template. So let me open here so we can see that. I'm going to close here. Oops. You all are seeing the ADI template, right? Someone just say yes for me.
Yes, we see it. Thank you.
Okay. So, and see, we have the cluster. You can see for each cluster, all the countries that are included in the cluster. For example, cluster 1, G1, is Afghanistan, Libya, you have all the clusters. G2, Albania, all those countries there, Ukraine. Cluster 3, it's in Africa. So you have all the countries here if you are curious about it. Here, that's our cluster here in Latin America. You have all those clusters here. So in this template that is available at the WHO website and FAO as well. So Uruguay is together with Australia, Bermuda, Finland. I don't think this is really fair because I don't think Finland people eat as much as meat as Uruguay and Australia. But here you see Uruguay is used UK, Switzerland, Norway, and then you have G2. So these are, so here we can, there is a manual to use this. I hate manuals, but here's the most important thing. So when you open these, I don't think I did that. So what I'm going to do, I'm going to close. So you're going to see, actually, I'm going to close and I'm going to open it again. So you can see what you have to do. When you open the template, it will ask you to habilitate the macro. So you should habilitate, otherwise the macro it will not going to work. Okay. So you habilitate the macro. Are you seeing it or do I have to? Do you see the template or not?
No, I don't think we see the template right now. We just
No,
see
no se ve.
your video.
Yes, so I have to close it. And I'm going to go just to share my screen. I'm going to share my screen here, desktop, because I want to show you that you have to. And then I'm going to open again the template, and then you're going to see it. Do you see me habilitating the macro? Do you see the template, Jason? Now.
Yes, we see the template now. Thank you.
Yeah, you saw that I had to habilitate the macro because otherwise you won't have the information. So here you have to start by writing the name of the compound. Let's do metalaxyl again. It has to be in capital letter. You really have to follow the procedure. But I don't remember the metalaxyl number again. So let's put a number here, 254. And then you have to put the ADI of metalaxyl. I think it was around 0.01, but I'm not sure. I'm just guessing here. And then you start filling out all those STMR numbers that you derived. Here, I'm always gonna guess, okay? We're not gonna write. Let's say if there was a registration if there was a recommendation for the group of citrus fruit. There wasn't, but let's see it was assumed. So you have to go to the recommendation table and look for all the recommendations. So here you have the citrus fruit group, but here you can have the subgroups here. So sometimes you have, let's not put this citrus fruit group. Let's see, we did not have enough data to make a recommendation for the citrus fruit whole group. So we made a recommendation for the subgroup of lemons and limes, and then we made another recommendation for mandarins. We made a different recommendation for the subgroup of orange. And then all you have to do is go, yes, and here, that's enough for citrus group. And here, for example, I'm going to point out, let's see, we have a recommendation for palm fruit. Palm fruit is easy because it's only apple and pears. Let's see, we have a 0.7 STMR recommendation for palm fruits. And then, let's see, if I don't have a recommendation for palm fruit, I only have recommendation for apple. And I put a recommendation for apple here. And if I don't have processing factor for apple to juice, I put it here. But let's see that I do have a recommendation for apple juice. So I put not here, but I put apple excluding juice. And then I go to apple juice and put another number here. Because if I would just put including juice and including cider, I don't have for cider, it would assume a very high consumption of juice at the same level. You would assume that the juice and the apple contain the same residue, and we know that's not true. So here you have to exclude juice and put the STMR of juice, which was derived from the processing factor for juice here, which is much lower than the residue in the juice, in the fruit, sorry. So here you see, you have a number for apple and a different number for juice. If you did not have that number for juice, no processing factor was included, so we would just include everything and put here. But as we do have, normally we have, and for the case of metalaxyl, I think I have, I don't remember anymore, we just erase the information as soon as we finish. We actually exclude juice here, 0.5, and put a different number for juice, 0.02, for example. And then what you have to do is just to go, oh, I know, because I put a point here, it should be a period. Sorry. So you just have to go through the whole table here and find which recommendations you have for. So let's put here, again, the same. Here, if I put here, it includes must, dried grapes, juice, and wine. If I don't have any processing factor, I should include everything there. If I do have processing factor for some, I should choose here the ones that exclude, for example, dry juice. If I have, let's do that. If I have a different processing factor for raisin, which is dry raisin. If for grapes was 0.5, maybe for raisin would be 1, because for raisin it's always higher. So you just go through the whole thing. There are groups, subgroups, different groups of banana. Let's put a number here for banana. just for fun. But you just have to go through your recommendation table if there is recommendation. So you have our groups, subgroups, Brassica, the whole Brassica group. If you do have a recommendation for that, normally we don't have. So for example, remember for metalaxyl, we have a recommendation for the whole Brassica group. So we put that for sub. So you just go down to all the crops that the codex, there is a codex, and then you start with the rice, with the grains, maize, sugarcane, coconuts, peanuts. I just want to go mammalian for the animal commodities. You have teas, dry herbs here, and then you have mammalians, for example, yeah, coming from the recommendation that from cattle studies, for example. Normally, mammalian recommendation are very low, with the exception of a few pesticides. Yes, normally it's 0.5, 0.5. More in many cases for meat, you have LOQs, you have MRLs at LOQs. And here eggs. And here, although we never receive any data for fish or for honey. I don't remember having that data there. But consumption data is here, but we don't have residue data. Okay. So after you enter all the numbers that you have consumption data for, now I have to. And then you have, sorry, because here I don't see the make a table. Oh, it's here, sorry, I'm confused. And then when you enter all the numbers, you just press here, make an EDI. It will going to apply the macro and give you a final table. Hopefully it will work. Let's wait a little bit. Should work. The calculation is ready. Look how nice it is. Calculation is ready. So it will give you, here, this is a mistake, okay? It has this bug here, but when it transferred here, it did not transfer the ADI, but it used the ADI at its estimate the percent of the ADI here. So don't worry about this. This is a bug that Tringy from the Netherlands supposed to fix. But so now what we do normally, we just enter the number here manually. So what is the outcome? For each diet, it has the STMR, the diet, and the intake. Basically, multiply this by this number and divide and multiply this number by this number and have the intake. And we'll, for each commodity for which there was an STMR, add them up for each cluster, add them up. Here it says cluster 1, 2, 3, 4. It doesn't fit everybody. Here's 7 up to 17. Yeah. And add them up, add the total intake for each cluster, the body weight which is used, divide by the body weight in microgram per kilo per person, and then apply the ADI and express it as percent of the ADI. What you don't want to see here is a percentage of the ADI higher than 100%. So for this example, completely theoretical example that I have here, the percentage of the ADI was, it ranged from 6 to what was the highest percent of the ADI? 20 here for cluster 7. Highest percent of the ADI was for cluster 16, 70% of the ADI. Our final statement was, we state the range of the ADI came from 7, which was the lowest, no, 4 in G1, cluster 1 up to 70% of the ADI. In this example here, which actually happens in most cases, there was no chronic, the intake was lower than 100% of the ADI. There was no health concern for the exposure of metalaxyl-M. Actually, the real metalaxyl-M exposure, I think the highest percent of the AGI, I think it was 2% or 5%, was much higher, lower than 100, than 70. So that is the ADI calculation and the chronic exposure. Maybe we can stop here, and we have still about 50 minutes for some question up to now. If there are some questions there.
We have about 6 or so questions, and so if we have 15 minutes, I think we need to go through them, you know, just a couple minutes time. But I think the first questions might be in Spanish, I believe, or maybe it came from Veronica. Anyways, I'll pass it to Veronica to start the questions.
Sí, la primera pregunta fue realizada en realidad ayer de Ivania Morera, que quería conocer